Hi, this is Dr. Barno, and I want to give you sort of a slower introduction to sine, cosine, and tangent. Um, and so the situation we're going to look at here is a right triangle. So I've got one here, and I've color-coded the sides so that we can match them up to the names that I normally give them. Those names are in reference to one of the angles of one of the non-right angles of the triangle. So here's the right angle. But we're going to be looking at things from the point of view of this angle here, which is at the vertex A, which is named alpha. So from that point of view, from the viewpoint of this angle alpha, or angle A, the green side is called the adjacent because it touches that angle. The blue side is called the hypotenuse. It's the longest side of the triangle, and it's opposite the 90-degree angle. And the red side's called the opposite. Now, if I change this triangle, before I do that, sine then is based on the idea of similarity. If I don't change these angles, I get the same shape. So all of these triangles that I'm moving around, they all have the same shape because they have the same angles. They're all similar. And when you have similar triangles, ratios between the sides that correspond match up. So no matter what's going on, what the sizes of the red and blue sides are, the fraction of the opposite over the hypotenuse, or in this case color-coded, the red over the blue, will always be the same. And since opposite and hypotenuse depend on the angle we choose, okay, because if we chose a different angle, a different side would be the opposite, we would get a different ratio. So we say the sine of A is equal to the ratio of the red to the blue. We say the cosine of A is equal to the ratio of the green to the blue. And we say the tangent of A is equal to the ratio of the red to the green. So, and you can see over here what those numbers are. And it makes about sense. It looks to me like the red is about half as big as the blue. It looks to me that the green is much bigger than the red, so it has to be more than half, but it can't be as big as the blue, so we have to get a ratio that's less than 1, and it turns out to be about 84% of the blue. And finally, it turns out that the red is about 60% of the green. And that's what these numbers are telling us over here. And we can just test those. So why don't we just make sure that the ratio of the opposite to the hypotenuse is about 0.54. So let me just let me just put in what those numbers are. So the hypotenuse is AC. In this case, it turns out to be about 5.96. And in this case, the opposite is BC, which is 0.31. If I take the ratio of the opposite and I divide it by the hypotenuse, I get about 0.54. And you'll see that that's just the same. If I make this triangle bigger, those numbers, the lengths change, but this ratio doesn't, and neither does the sine. If I make the angle smaller, all the lengths change, but so do sine, and so does this ratio, and they always match. That's because the sine of an angle is the opposite over the hypotenuse. Okay? So sine is always the opposite over the hypotenuse, cosine is always the adjacent over the hypotenuse, and tangent is always the opposite over the adjacent. We have a little mnemonic device here, sohcahtoa. 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 And that's a mnemonic device to help me remember that sine is the opposite over the hypotenuse, so SOH. Cosine is adjacent over hypotenuse, CAH. And tangent is opposite over adjacent, TOA. So why know these things? Well, they become very useful if I'm trying to understand sizes of inside a triangle, and I only know a few things. So let's imagine that I know that the angle is about 24 degrees. And I know that the hypotenuse is 10.25. Then, using the fact that I can go to my calculator and type in sine of 24.06 degrees, I can take that, and that tells me then that the opposite side is about 41% of the hypotenuse, which in this case I know is 10.25. So if I take 41% of 10.25, I should get the opposite. So I'm thinking that based on the ratios of sine and cosine and tangent, that the opposite will be about 4.18. Let's see if that works its way out. Oh, yep, it totally was. It was 4.18. Hooray! What about, could I figure out what the adjacent is? So 10.25. Cosine is telling me that for an angle of 24 degrees, the adjacent side is about 91% of the hypotenuse. So I'm going to say 91% of the hypotenuse is the adjacent, 9.36. Let's see if that works out. Sure enough, 9.36. We're exactly what we thought it would be. Let's just look at how sine and cosine and tangent change as I change the angle. Okay? So I'm just going to lift this point up and down. So as the angle gets bigger, you can see sine's getting bigger, cosine's getting smaller, and tangent's getting bigger. In fact, tangent is, since sine and cosine are over the hypotenuse, and the hypotenuse is always the longest side, tangent is the only one that can be more than 1. And if tangent's more than 1, it means that the opposite side is bigger than the adjacent. And you might have noticed where it changed over from being bigger than 1 to smaller than 1. It changed over exactly at 45 degrees. 45 degrees is when we have an isosceles right triangle, and so they're equal. So these numbers, these tools, sine, cosine, and tangent, become very helpful in figuring out the sizes of various parts of triangles, and basically an essential tool. So let me just show you one more time how I might use them. This time I'll show you with my calculator. So let me set up a sort of big angle here. How about 51 degrees? And in this case, I'm going to know that my hypotenuse is 11.17. Let's say I wanted to figure out the red side. Which of my 3 functions do you think I should use? I know the hypotenuse, and I want to figure out the red side, which is the opposite. Well, I can look at, so think about it a minute. I can look at sohcahtoa. Opposite and hypotenuse are part of sine, so I'm going to use sine. So I'd go to my calculator. And I would say, let's figure out what sine of 51.04 degrees is. It's that number there. So it turns out the opposite side is about 77.7% of the hypotenuse. So I'll take that number and I'll multiply it times my hypotenuse. I get 8.685. So about 8.69. That's what I think the opposite side is. Let's see if that works. 8.68. So close enough. Okay. How would I figure out the adjacent? Well, to figure out the adjacent, I know the hypotenuse. I want to know the adjacent. That's A and H, so I'm going to use cosine. So cosine 51.04. It tells me that the adjacent is about 63% of the hypotenuse. So I take that number times the hypotenuse, get 7.02. Let's see how correct that is. Dead on. If I'm going to use tangent, I won't assume that I know the hypotenuse. In that case, I'll assume I know the adjacent. So we just figured out the adjacent was 7.02. With the tangent, I'll be able to figure out the opposite. So if I know the adjacent, I can figure out the opposite. How would that work? I would say tangent of what? Well, that angle. That angle defines the situation. Okay, it turns out that the hypotenuse in this case is about 124% of the adjacent, so bigger, the same size and then some more. So I multiply that times the 7.02, and there's my 8.68 again. So I hope this helps you with some ideas about how sine, cosine, and tangent work, how to use them to compute different sides of a triangle, and how they are based on the ideas of similarity.